All right. Hello, everybody. We are right on time. Welcome, everybody, to the Nice Talk 150. Today, we are honored to have Yufan from UC San Diego to share his work, Test-time Recursive Thinking, Self-Improvement Without External Feedback. So this is a work collaborating with Microsoft Research. So we know recently lots of language models have shown very good improvements in lots of capabilities, but mostly they are driven by reinforcement learning with some verbal rewards. So with some verifiable rewards. So basically today we are going to learn from this work and discuss how can we make these language models self-improve without the need for additional training. So our speaker Yufan is currently a PhD student at UC San Diego. So quoted from his website, his research focus is trying to make language models reason better and more agentic. And he's also focusing on some related areas like large model reasoning, agentic learning, and multimodal learning. And he has lots of experiences in industry, such as Internet, MSR, Apple, Meta, etc. And I think he will also introduce more about his background later. I'm today's host, Haolun. So we are right on time, so you can share your screen. It's all yours.
Sounds great. Thank you, Haolun. Let me share my screen first. All right. Yeah, thanks for the intro, Haolun. And I'm honored to introduce our talk here, our work here. It's called Test-time Recursive Thinking. Basically, we're trying to see can the model, as smart as they are, can they try to learn from their own interaction with the world, try to write down some knowledge, and without any feedback from like the ground truth, can they reason better? That's the main focus of this work. And a little bit intro about me. My name is Yufan. I'm glad to be here with you. Currently, I'm a final year PhD student at UCSD. I used to be a research engineer at IBM Research, and throughout my PhD, I have interned at different places, Microsoft Research, Meta, AMD, Apple, and most recently, I'm at the Microsoft AI's post-training team. Yeah, so like my focus has always been like how to make model learning to learn. I think that's like one final step towards AGI is like, how do you build an intelligence that can adapt to new challenges, like rise to the occasion, as we say. So I think we're very close from my perspective to building something that can adapt to real world challenges, at least from my observations. But like, it's hard to say how fast we can close the gap, but like, it's an interesting world to be in right now. Yeah, so like nowadays there's like call this, call that, like all the time you heard these things, like as an agent, you want it to grow with you without training it, because like you're just interacting with your agent, with your AI, with your personal intelligence on the edge device, typically a computer or a phone, and talk with it, do stuff for you, right? Either writing code or doing some, like booking a restaurant, like buying flight ticket for you, stuff like that. And sometimes you'll tell them like you did it right or did it wrong, but you don't want it to like repeat the mistakes all the time, right? So in this work, it's like, can we somehow find out like what matters for the model to learn from its own mistakes, what helps, and what's the best way to build this recursive thinking framework around like strong model. And the three motivations for this work, firstly, needless to say, tokens are much cheaper than humans are. You can have millions of tokens at several dollars, but hiring a human to do work for you would pay easily much more than that. So ideally, you want to use as much as tokens as possible, right? That's cheap, and you want to only have human judgment at like minimum like requirements. You want to use like this amount of human effort to achieve the biggest possible results. Also, the models don't have infinite context limit, although they are growing at a fast pace. If you are using Cloud Code these days, it grows to 1 million tokens. That's quite a lot, but still they're finite, meaning that you cannot just throw everything into the context and expect the model to learn from the context naturally. Somehow this context is a resource, and they are gonna exhaust if you do it this way. So ideally, you want to have some knowledge that's condensed, and you can pass them over into different rounds. Like when you do more thinking, you want to condense them, then in the next round, start from there instead of starting from scratch. Also, ground truth feedbacks are hard to get. Typically, like whether it's like solving a problem or doing something for somebody, right? We are interacting something for a user, right? You cannot constantly ask them, did I do it wrong? Did I do it right? Like sometimes there's no way to know it at all if you are solving some open science questions. So the system should be training free and ideally adapt on the run. These are the three motivations for it. Really, it's like, how can we use something that's cheap, like we can think as much as possible without like knowing the ground truth? How can we build a system that like reason like a human being, if you think about it? We write books, we write papers, right? These are documentations. We don't know if they are like 100% right, 100% wrong. You just kind of know it. They're natural science, stuff like that. And we build on top of this. So I think in the future, this might be I think a big breakthrough might come from these like knowledge recursive things. So yeah, this is collaboration work with my mentors and colleague at Microsoft Research. Thanks for them. We can finish up this work. It's test-time recursive thinking, self-improvement without external feedback. The framework, test-time recursive thinking, or as we call it, TRT, is really built on top of two basic and I think simple ideas. First, like you want to have a knowledge list, right? Like I said, people write books, write papers. You still have some sort of like memory per se. When you are going from round 1 to round 2 and round 3, you want to carry out some of your findings in this format, right? So we call this knowledge list. In each round, we'll have 3 steps, right? Each step consists of like, first of all, you're given a question, you're given a knowledge list, and you have these parallel thinking things into it. You can devise different strategies for different rollouts because you don't want the strategies, you don't want the rollouts to be repetitive. You only have so much compute. You cannot waste it on, like solving it for k times, and most of the solutions are mostly the same, right? That's going to be meaningless explorations. So the model should devise a strategy for each rollout. Afterwards, the model will, without knowing the ground truth, rank the rollouts by itself. It will use a certain set of criterions devised by itself to rank them. And think of this as in-context GRPO. Instead of extracting the average, then try to calculate this like difference in this discrete token space. What we do is we pick the best, right? So model select some solution as the best solution, and we try to ask the model, what's the difference between the best solution and this lesser solution? What's the gap there? What did that solution do wrong, right? And ideally, the model should be able to say, okay, I look at both solutions and I can see where this gap is coming from, right? It's maybe coming from if we're solving a code problem, it's like this boundary condition is miscalculated, and this should be put onto the knowledge list. So next time, when I'm devising, such solutions, I won't make these mistakes, right? So this is constitutes one round of thinking. And you can do this round and round until the model is happy with it, or you exhaust all your compute, stuff like that. So really a 3-step framework. First, try to devise the solutions. Second, try to rank them. Third, try to say, can I extract something from these rollouts without knowing the ground truth? And there has been lots of related work on this domain. We have these like meta-RL paper. Train the model to explore and adapt with this like meta-learning objective. We have these agentic context engineering. They try to also build knowledge over the iterations. We have these parallel thinking. We sample multiple rollouts, and somehow with some mechanism, we do better than majority voting. So this work, I consider it as a blend between, I think, agentic context engineering and parallel thinking, because like really we have this ability to do parallel sampling. How can we better utilize that, extract things from it without training the model? Like I think a big part of it is how can we do this training free? And our main findings are twofold. to make this effective self-improvement system, you kind of need two things. One, as we kind of elucidated a bit earlier, we need some exploration mechanism. It should be efficient, right? So there shouldn't be any repetitiveness in it. It's like a search problem. You should cover the search space as fast as possible. And then you need to have like a reliable selection mechanism. So without knowing the ground truth, the model should be able to somehow separate the good from the bad, right? Somehow be able to know this is a great solution and like this is a not so great solution. And we're going to show how different mechanisms like designs would affect the model's final outcome in this recursive thinking session. So for the exploration, what we propose is pretty, I think, straightforward. One is this for rollout strategy. The model should decide, right? When I'm telling you, you have two chances of solving this thing, what are the top two you think solutions that are going to solve it most likely? You can come up with 10 and pick two. Right? You can do these pre-thinking, let's say, right? Design the strategies first, and later on carry out your strategy. And then you have this knowledge list to write down what was working, what wasn't working for you. So ideally, you should have a smaller search space after round and round of thinking. And it's worth noting that we found that it's more important to write down what wasn't working, right? So the wrong solutions compared to writing down what was working. So for the models, we observed that if you write down what was working, right, the right solutions, it kind of discourages the model from doing more explorations. It's like, yeah, I just know it's gonna, like, this is the best way to do it. I'm just gonna keep doing this. And sometimes it's really not. Like when you're proving something in math, solving something in coding, some steps may be mistaken, right? Sometimes it's like a subtle mistake. But if it's like included in the right solution model, we're just blindly following it without knowing there's an alternative, more correct way of doing so. So I think that's one first like very interesting empirical findings in the exploration strategies. Then we're gonna go to the selection mechanisms, right? When we talk about reliable selection mechanism, there are two things we take into consideration in our design. Firstly, we don't require the model to provide the exact ranking, right? It's not like you have to rank them 1, 2, 3, 4, 5, right? It's like which one is the best. It's much easier that way and much cleaner for the learning signals. You can make these pairwise comparisons. Vice versa, like you can do something more complicated. Let's say you build a rank list and try to say what's the difference from rank 1 to rank 2, rank 2 to rank 3, or rank 1 to rank 3. You can do these combinatorially and see what kind of knowledge can you extract, right? But selecting the best, we find it to be easier and more reliable to learn from. Then there are domain-specific things you need to do. For math, what we do is, because we are really solving these competitive Olympic math problems, right? We have a finite number of solutions, so they are mutually exclusive. The answer to a certain problem cannot be 32 and 62 at the same time. So if a model now says the answer is 42, you have to find a reason, solid reason to reject 62, let's say. What's the last round's answer, right? So gradually the model will learn from this back and forth, rejecting the wrong answer, picking the right answer, and rejecting one requires a solid reasoning, right? So while doing so, it gets some sort of learning signals, some sort of self-correctness in its own, like the proving of this is wrong, this is right, do require it to carry out correct reasoning in the meantime. And for code, it's much harder because answers are not mutually exclusive. For solving a code challenge, there are many ways to solve it. And even under one solution, one way, one algorithm, you can implement it in numerous ways, right? All of them might be correct. So you can no longer use this mutual exclusiveness to reject answers and ask model to say, okay, if you reject this one, provide a reason, right? There's no way to do this. So we let the model to write its own test cases. and let the model to like run these test cases, see what's the outcome, and are they differing from the expected outcome, right? This provides a twofold benefit. First of all, needless to say, they get to see how the code actually runs, right? Given the real, their self-generated test case. And then it's like in the interviews, when the interviewer gives you this, like, oh, then can you design a test case that's gonna, test for the correctness? The model actually think more, right? It's like, what are the counter cases? They'll take these into consideration into, building these algorithms. So it's another kind of side effect, calibrating their reasoning towards the correct solutions, although they do not see the right answer or like the ground truth test case in this coding settings. And here we go to our main results. I consider the main results to be pretty strong. So we show that we can use two state-of-the-art open source models. We do this round and round of thinking, test-time recursive thinking on AIME 25, which is 30 questions for Olympiad competitive math challenges. We show that about 20 rounds of thinking is enough for the model to reach 100% correctness, which means they are able to solve for like all of these problems and remain quite stable at that level, comparing with, let's say, majority at 64, right, which is what you do with typical simplest way of parallel thinking. And we show that for closed source models, for GPT-04 mini, for 03 high, with test-time recursive thinking, it can boost the performance to 10% or about 15%, much better than the baseline and on the hardest part of the LiveCodeBench V6. And it's surpass the performance of RSA over the same compute 8 rounds. So these are the main results that we have. Shows pretty strong performance boost without accessing the ground truth knowledge or the actual test case, stuff like that. It's like you can trade for better performance with stronger, higher need for compute, right? Basically, if you can expedite more compute, can get more performance, which is like pretty nice thing. And we're currently limited to code and math, which are strongly reliable on reasoning. But like in the future, we are hoping if we can make this to general domains, stuff like that. Another thing to think about is how to make things generalized. Let's say you're solving this coding question, right? Instead of thinking things only specific to this specific like coding question, this is like a dynamic programming one, and you extract some generalizable failure patterns, right? You can learn from them, and hopefully for solving similar problems in the future, or in general solving coding problems, or in a more general sense, solving these logical puzzles, you can avoid a certain type of mistakes, right? So these are things I think also remains interesting going beyond coding and math. And we also have some more in-depth analysis of the model's behavior, like I said before. First of all, we like to see, do our proposed strategies and our proposed knowledge list speed up the exploration in that solution finding space, right? We compare with TRT and the baseline, which is sampling parallel at pass k. We measure the performance in that metric. We compare that for round 1, let's say for TRT with a beam width of 2. So each round will roll out 2 solutions, right? So we'll compare with a pass at 2 for round 1. So for round 2, we'll compare with pass at 4, right? And for round 4, we'll compare with pass at 8. We show consistently with TRT, there's a performance boost, right? Because obviously you now have this acquired knowledge of like what's more likely to be working, what's more likely to be failing. And also you don't waste compute on trying the same stuff over and over, right? So there's a clear gain from that. Secondly, we like to see, given a finite number of compute, do you really want to do more rounds? Or do you want to do more width? Like, do you want to do stronger parallel thinking, or do you want to do more depth, like do more rounds into this TRT framework? We show that typically width of 2 is already good enough when you have more rounds to expedite. And if you only have a limited wall clock to wait, you don't have too many time to wait for the rounds, you can probably start with like a medium to high level of width. That would be a good solution if you only can do like, let's say 2 rounds or like 1 round. And thirdly, we want to see how much does this self-verification, self-judgment signal matters, right? I mentioned before the model can devise its own test case. And one quick alternative to that is let the model look at the code and do some basic reasoning. Let it just look at it. And as a competitive coder, like it may be able to just read their code and understand which one is better, right? And which one would be worse. Right now, I think the model are not there yet. Maybe in the future, they are able to be like that, simulate how the code will execute in their mind. And it's going to correlate 100% with reality. But right now, there's still a gap. So it needs these self-generated execution to go beyond, plainly just looking at it and thinking about it. So thinking at it give you about 3% performance boost, but if you let it to write their own test case and try it out, you can do 10 to 15%. And then we want to see how much of the context this knowledge list is taking, right? So with this system built, you don't want this thing to grow and grow and grow and eventually take up all of the context of the model, right? That would make it kind of useless. We show that for math, for code, they typically take up to about 1% of the context, which is not a lot. And if you think about it, they stop growing after 16 to like 32 rounds. Like the curve is relatively stable around that one. So meaning that you don't make too much adders to the knowledge list at a certain point. It kind of stays that way. Of course, you can add in these pruning strategies if it grows too long. But like just purely from our experiments, this simple version of it would already work quite well in practice. And lastly, we can do some qualitative analysis of the model. What kind of knowledge are they really writing down, right? So for coding, we have most of the knowledge related to the performance of the code, meaning that they will write down things about like, oh, this is not running fast enough. This is taking up too much memory, right? Stuff like that. These are mistakes to be avoided for that reason, right? Or indexing. So for dynamic programming, there are lots of errors about indexing, and they write these down so they can avoid them. And lots of them are about edge cases, because like really for these programming stuff, you have to be aware of these edge cases to be able to succeed, to pass through all of these test cases. And so they have something about algorithm, the numericals, the bug fixes, and the IO format, and 14% is related to other stuff. And then have a deeper look into what kind of problems are being done correctly, and does the model, how much does TRT help, right? So throughout the 8 rounds, we see that 93 of the problems after about 200 problems are originally correct, right? So they are already correct in the baseline. And 57 of them are newly solved by TRT. 31 of them are unstable, meaning that sometimes in the round and round of thinking, at some moment, there's like a moment of delight. It's like, oh, the model solved it. But then at some point, they propose an incorrect solution to replace the correct solution. So sometimes it's like that. Sometimes it goes into like a cycle, stuff like that. So it's not stable. It's not stably correct. And then until the end, it falls into a incorrect solution. And about 22%, 22 problems are too hard to be solved. So they are never solved throughout the TRT practice. We can then take a closer look at their strategies. So for each round strategy, we can kind of compute the semantic closeness of round one strategy and round two strategy. How close are these, right? And since we have access to the ground truth test case, we can actually test for these round rollout, is it correct or is it incorrect, right? So on the left side, these are for the failed solutions. So last attempt was actually a failure. And we see that although do want to try new stuff, 82% of them are new strategies, are more like different things to try on. And on the right hand side, we have the last time attempt is actually succeeding. Model is more inclined to refine on a previous strategy, which shows that without the ground truth, model can somehow know they are working towards the right direction. And then we have the correlation between the depth of exploration and the solve rates. So on the x-axis, we have the number of unique technique clusters. Basically, we're trying to measure the number of distinctive techniques tried in the different kind of strategies tried throughout the TRT loops. And then we observe that the more stuff you try, it's more like you get it solved, right? So which is kind of making sense, and we find it to be a positive signal that model is able to propose various things and try it out and eventually pick the best solution from them. So that's mostly the main analysis of the paper. We find out different things about different parts, what matters for a successful recursive thinking mechanism, right? Number one, we need a good exploration strategy, right? So, and then you need this accurate ranking and selection mechanism. I would actually call it semi-accurate because without the ground truth, all you can do is provide an environment for the model to play with, right? Imagining if the model is only speaking to itself into the void, there's no feedback at all. Model can only think about it and getting nothing comes back at it. It's going to be extremely hard to evolve. Essentially, you're playing with an environment that you don't know the state, how the states are. Then for the fast exploration, we show that it's more important to avoid the previous mistakes, and for the rollout, ideally, you want to make it, right? Because you don't want them to repeat. So device strategy matters the most for that case. For the accurate ranking and selection, you need to select the best and also devise some sort of domain-specific signals to it. So that concludes this work. I think that's a findings type of work. We try to look into how the state-of-the-art models are performing when they are given this test-time recursive thinking tasks, right? So for solving coding, for solving math, we show that the current good models are able to do this. They can improve their performance, and we try to see what matters the most for them in this recursive thinking loops. I think personally, this knowledge accumulation would be the next big thing, or already a big thing right now. Ideally, you don't want to train this model over and over when it's with a different user, you train a different version of the model. You kind of just want the model to have access to the user's previous history and try to learn from that, right? And ideally, when you deploy it for coding, sometimes it's going to be able to see, oh, this solution is failing for this repo. Why is it failing, right? You can look at it and try to gather some sort of memory for it to do better next time. And I think the big part of this work shows that this thing can be RL, right? So you can have this evolution strategy and have this retrieve, react, reflect loop. This thing all going hand in hand with RL. You can do this one pass of this, and sometimes in the future, throughout the rounds, at the end, sometimes you can see the model is able to engineer its context to make the code work, right? To find the right solution for the math or for the domain-specific task it's able to solve for it. you can give them some sort of reward, right? So this is totally doable. And right now, I already see some sort of work in this direction that tries to train a model to do this context engineering with RL, and they are quite effective. And throughout this framework, I'd say, or this class of framework, the key choices are also like, how do you condense the knowledge, right? Are these your like skills? Are they your MCP server for you to access? Are they like a vector database to search from? And for the RL environment, do you solely use it for coding or for to use? Or it can be a general domain, like without a domain specific thing, just be doing something, and the model can just like learning to explore and to condense knowledge and adapt to the environment. I think once we can get this done, that's really the new era of small models. Because I think right now, this work only works for big models. They need to be trained extensively for having these like base knowledge or base capabilities. But if you have a small model that can accumulate knowledge and learning from them, that would be an amazing thing, right? Because essentially, all you need is to deploy this thing into an environment and gather stuff. Gradually, it will be better to learn to use these tools. It doesn't have to be trained into their parameter space, right? Or have every knowledge in their parameter space. You can try to learn to use these tools to get the knowledge that it requires. So that concludes the talk. I welcome any questions from the audience, if there are any.
Cool. Thanks, Yifan, for the great presentation. I think this is a really interesting work. And also for our audience, if you have any questions, you could post it on any platforms you are using now. So maybe I can start from some of my questions. I think actually the motivation is very clear and very, the full logic is very clear and it's very, seems very usable. Maybe I will start from about the rollout strategy, because I think a very good design of your TRT is for each rollout, you have a different strategy, right? So I just wonder, in practice, how do you know these strategies truly cover different regions of the solution space, rather than, for instance, they are similar to just being superficially different prompts that still induce very high overlap recently? Like, is there any mathematical guarantee or it just work in practice?
Yeah, that's a great question. I think what you're asking is like, suppose the model write out different strategies in the semantic space. Are there any guarantee that solutions are actually different, right? So that's the question. And I think from my own observation, it does lead to different solutions, because like the strategy would be like, oh, this trying to devise a dynamic programming, right? This is trying to devise a greedy solution, and the model will follow suit to devise or to write a code for that. But empirically, we don't have a metric yet to directly measure like the similarity in the code space or in the math space. I suppose we can do something in the math space. It's either that way. For the code space, we do need to have some sort of similarity in the coding structure or something like that. Have a formal measurement for that. But that's a great point.
Yeah, got it. Makes sense. And also, I think also intuitively, right? If you change to a different strategy, definitely it should be better. It should be more diverse than using the same strategy, but simply sampling multiple times. Yeah, I fully got it.
Yeah.
And also one thing is, I read your paper. I found in your limitation, you mentioned one term called like a residual selection gap, right? Actually, could you please elaborate more on this? Because since we have more time for discussion.
Sure. I think that points us to this selection strategies, because these are not perfect emulations of the actual reward feedback, right? So like you're interacting with the environment, and you don't know the kind of reward you're getting for the ground truth, right? You don't know if you're doing something wrong or doing something right. What you're interacting with, like mentally, I think of this math model is like you're getting some sort of noisy feedback. you construct something to approximate the actual reward you're going to get. And this approximation is actually a biased one because it's based on how the model think about this problem. It's like, it's supposed to be solved this way, so it should give me this kind of feedback, right? And it will lead to big problems, let's say, because it's only an approximation. And it's like the more hallucinated the model is, it's going to actually deviate more from the ground truth because the reward is also going to be hallucinated. Like it's like a feedback loop. It's going to only kind of strengthen the echo of the hallucination, let's say. So that's what I'm talking about over there. If we can somehow have an RL strategy to reduce that gap, it's like a word model of like simulating how the word will behave or will perform under different kind of like interactions with it.
I got it. Because for the first time I read it, I was just thinking like, where does this gap mainly come from? So for instance, I was thinking like whether it mainly comes from insufficient candidate quality, or the verification is imperfect, or the model actually generates a correct solution but failed to select it. So I was just thinking about this.
Yeah.
Mm-hmm.
Yeah, it's like, it's kind of a paradox. It's really if you can have a perfect feedback mechanism or a perfect selection mechanism, right? The model can devise something like that. It's equivalent to like the model knows how to solve this, right? The model knows how this should be solved, right? So I think the funny thing is how to formally define the challenge of this problem, because like model is doing these own approximations. From all these literature from like weak supervision, we can learn that even if the feedback is noisy, even if you're learning from wrong labels, you can somehow still boost the system towards maximum performance, right? So under the proper assumptions in the classical weak supervision setting. Right now, this is like weak supervision in RL. How do you formally define it such that even though the reward is biased or it's like noisy, is there a smart way to build a system based on this theoretic foundations so we can self-evolve or allow the model to be able to work in this format? I think these are many like interesting questions to be solved for the
Exactly, I agree. Yeah, super interesting. And also one thing is, I think one of the application or one of the data set scenario you're using is about coding. And I feel your observation to me, I feel it's also very interesting. Like you found most accumulated knowledge is about performance, edge cases, and indexing, right? But not the algorithms. Is my understanding correct? So I feel this part is very interesting to me. I just wonder how do you interpret this? Like for instance, is it an evidence to show that strong models are actually currently bottlenecked less by algorithm design, but more by this kind of execution level, how should I say, robustness issue? So is that correct? Or like I want to hear your understanding about this.
Yeah, I think that's exactly right. It's also tied to one of my previous like questions. It's like, how can we divide the system to extract generalizable knowledge? So the things you're pointing to, right, indexing errors or like implementation mistakes, these things do happen for the strongest models. Like right now, the frontier models, they're still having these issues, especially for, these computational problems, they're tricky. Sometimes they're designed, you have these like spots, like if you didn't think of these edge cases, you will fail. So they are tied to these, but like failure to see a generalizable pattern, I think it's discouraging in the sense that these things won't be usable for other problems. Like you solve for these, you extract this knowledge, but it's completely useless for different problems. If we can somehow find a way to make these things extractable. I think one really interesting thing I'm thinking about is using some sort of like rubrics. The model can think of self-devise a rubric to rank them, right? And then these rubrics will be transferable. It's like how do you grade this code, right? How do you grade this math? And if the model can devise an accurate rubric, that's actually more like having a more accurate feedback system from itself, and it's more transferable in that way. But yeah, these are I feel like lots of these are empirical research. Yeah, it's like how do you try things out? How do you play with it? What's the term for it? It's like agent harness, like experimentation, stuff like that. So all you can do is have some intuitions and go for it. Exactly. That's what I think right now.
Exactly. That makes sense. Actually, I think I'm good with this work. I think it's super interesting. And maybe I guess we still have time. So currently, I don't see any audience posting questions online. Maybe we can discuss more. So like at the very beginning, I was also thinking like in this paper, TRT is just used as a test-time scaling, right? I think maybe you also mentioned this. So probably we can also motivated by RL or something, we can train it, we can treat it as a training objective as well, right? Like, for instance, maybe we can, distilling this kind of recursive thinking process back into the model itself. So to fully, to better improve its capability. So maybe that's also a way to do that, right?
Absolutely. I actually wrote code and run experiments to try to do that. The execution, like you said, is straightforward, right? You do this TRT and you try to observe after several rounds. Do you get a performance gain, right? Did you correct or wrong, right? Did you get these, or actually you run the correct one, right? You were correct at a certain point and you mistakenly rejected it, right? So these are very direct learning signals, and of course, the generation of the strategy and also the knowledge accumulation steps. These are model generating tokens. You can GRPO them or whatever you do. It's straightforward. The challenge really comes from the system optimization side, because like from our experiment, we see only strong models, large models have these recursive, like reflective behaviors. You can only have these 120 billion OSS, CPU OSS, or like the largest size of the Quinn models can do this. Training them, it's a very resource intensive thing, right? I tried a little bit, but I decided to like leave this massive training work for more industry lab people to work with this.
Pretty sense. Cool.
Yeah.
And also maybe one last thing I'm very curious about to listen to your thoughts is, I think you also mentioned like one future direction is probably consider about from a single instance knowledge to cross instance knowledge, right? If I can say like that. Like basically, I think the aggregate knowledge across problems rather than within a single instance. So I just want to hear your thinking about this. Like, what do you think the biggest bottleneck on this? Like, is it how do you do the right level of abstraction, or like how should I say, mismatch of the failure modes across different tasks? I personally don't have too much knowledge on this. I just want to listen to your thoughts.
Sure thing. Yeah. So these are purely empirical things. I find one methodology to work quite well for me is I try to separate the problem-specific things, right? These are failure modes for like solving the dynamic programming or stuff like that, right? These are problem-specific. And there are something from like psychology, you can say these are meta-cognitive skills. This is like how to think, how to reason, how to learn. I find that if you separate the knowledge from these two parts, one is devise something to guide your knowledge as like foundational principles of thinking, of like solving coding problems, right? And then if you say for this problem, you have these specific things, so and so, there's maybe hope to generalize those metacognitive skills to other problems of the same domain. But like this is like to be done. Like currently working on this. I hope I can bring up some more new results in the near future. But yeah, so I feel like lots of this exploratory it evolves with how the model are being built right now, how the state-of-the-art models are being trained for. It definitely matters what domains you're talking about. So it's a highly empirical kind of thing to try on.
Definitely. Looking forward to have you back again in the near future to talk about the major results.
Perfect.
Cool. I think everything is cool. Let me double check if any audience have any questions online. Yeah, so far so good. So I guess maybe we can stop earlier today, and I hope everybody enjoyed the weekend. And thank you again, Yufan, for the great presentation, for sharing this great work. And also thanks everybody for coming to this nice talk.
Sure thing. Thank you, Holder. Thank you for the nice team.
Thanks.